Alrighty. Hello, everybody. My name is Zach Brumbach, and I'm one of the linear TAs. Unfortunately, my big review session did not have audio, so I'm just going to do an abbreviated one here for the second midterm. So I'm just going to go through a few of the questions I did last night and then some of the big picture topics as well. So to start for midterm 2, there's a few things that are there's a few big things that are going to be on this. First of all is column space and null space and everything about them. And then the other big topic is onto and 101. And then with this is subspaces as well. Kind of a subtopic of these things is domain, codomain, and range. And understanding these kind of locks down all the different things that this exam is about. And within this, there's also another subtopic of a basis. Okay. So first, I'll talk about column and null space. Column and null space is just the things that we did for the first exam with a different name. Okay, so typically what is being asked is to draw a column space, to draw a null space, or to find a basis of either of those two things. So the first question is, what is a basis? And a basis is the smallest building blocks for a space. And what I mean by that is the smallest building blocks, a basis is usually composed of vectors. And for this class, they'll only be vectors. So what this means is if I have a plane has a basis of two linearly independent vectors in the space. So there is a basis theorem, and what the basis theorem states is that to be a basis, the vectors composing a basis must, one, be inside your space, and two, have as many linearly independent vectors as you have dimension. In this case, a plane is 2D, so we need two vectors. For example, if it was a three-dimensional space, we would need three vectors that are all linearly independent, and so on and so forth. So another important thing to note here is they must all be linearly independent. And what I mean by that is if you have three vectors and only two pivots, those are not linearly independent. So when being asked to find a basis, you're always going to start with a matrix A. And then in this class, the first thing you should always do is put it in reduced row echelon form. Always, always, always. Okay, or at least when in doubt. From here, if we're looking a basis for the column, let's call. We're looking for a basis of the column space. What we do is we go from reduced row echelon form and we find our pivot columns. Okay. And from here, the pivot columns of original A, or the pivot columns corresponding to the columns in the original matrix A, form our basis. So what I mean by that is that we have a 4x4 matrix, or sorry, a 3x4 matrix. When we row reduce this, what we're going to get looks like where this is a pivot and this is a pivot. Basis for this matrix would be the vector correspond to my original matrix. So the basis for the base of this matrix A would be 1, 2, 2, and 1, 1, 1. And we usually put them in this little like curly bracket notation. The curly bracket is around the vector. Now we need to talk about the basis for a null space. So from reduced row echelon form, we go from here to parametric vector form. From here, the vectors in parametric vector form our basis. going back to talking about this A over here, if we once again have that matrix 1, 2, 2, 0, 1, 2, 0, 0, 0, 0, 0. We're trying to find the null space. What we have equals negative 2x2 minus 2x3. x2 is free. x3 is free. x4, this one's a little tricky. This is equal to 0. So this gives me the parametric vector form, x vector 2 times negative 2, 1, 0, 0. Plus x3 times negative 2, 0, 1, 0. Okay, so the base here would be these vectors. So the basis for my null space is negative 2, 1, 0, 0. And I'll write it in the same format I wrote the last one. And negative 2, 0, 1, 0, parentheses with our curly brackets at the end. And so is dependent. It would be linearly independent. And the reason that is that for x2, in all of my the one with x2, if it doesn't make sense, don't dwell on it too much. Just kind of know that those vectors will be independent from there. The basis in null space, the basis of column and null spaces, and just as a reflection for what the shape of a column space and null space is going to be, it's just going to be like our span. So for column space, it's going to be number of pivots, dimensional in the number of rows. And a basis for our null space is going to be number of free variables, dimensional in the number of columns. So if we wanted to like quadruple check this, our matrix was originally 3 by 4 with 2 pivots and 2 free variables. So we have 2 pivots, so we should have 2 vectors in our basis of our column space. We're going to get 2 free variables, so we're going to have 2 vectors in the basis of our null space. Just to make sure that dimensionally we're right, that doesn't really confirm the numbers at all. Okay, so that is column and null space. Now I'm going to move on to talk about, I'm going to talk about subspaces first, and then we're going to talk about from here going into the onto and one-to-one stuff. So subspaces. Okay, there's 3 rules that govern subspaces. Rule number 1 is 0 is contained. Number 2 is closed under addition. And the last one is closed under scalar multiplication. So multiplication by a constant. Okay. And the most common subspaces we see in this class. So some easy examples that if you can describe them like this, they are automatically a subspace, is a column space and a null space. These 2 things are always subspaces. And a little sidebar here, any solution set to AX equals B, where B is not 0, so we're looking for an inhomogeneous solution, this is always not a subspace. Okay. So to now talk about what these 3 conditions mean is geometrically first, and as well, geometrically, for example, if I have a graph, I have a line on this graph. To check if this line is a subspace, we must check if 0 is contained. Do we touch the origin? In this case, yes, we do. Secondly, closed under addition means that anything on this line added with anything else on this line will remain on this line. And that's true. And for closed under scalar multiplication, if I have this vector and I multiply it by any constant number, it will still remain on that line. So all 3 conditions are met. And if all 3 conditions are met, it is called a subspace. If any one of those conditions is not met, it is not a subspace. Okay, so an example of something like this that wouldn't satisfy those conditions would be if we're solving an inhomogeneous solution set. So we're going to have a shifted line, for example. Okay, now we're checking our three conditions. 1, do we contain the origin? We do not. We can already say it's not a subspace. 2, if I take any two vectors that are on this line and add them together, am I going to still be on this line? The answer is no. So this is not closed under addition either. And then lastly, if I have some vector here that corresponds to some point on that line, if I multiply this by any number, you will not remain on that line. For example, if we multiply by 2, we're way up here, not on that line anymore. This is not closed under multiplication either. So an inhomogeneous solution set is none of the conditions and definitely not a subspace. So this is how you think about it maybe geometrically. Another example that people see a lot is an equation that looks like this. Given x and y in R2, so this would be like talking about a space given a condition that x, y equals 0. And we're asking, is this space created by this condition a subspace? Well, if we were to think about this equation here, x times y equals 0 means either x is 0 or y is 0. So that means my plot is the x-axis when y is 0 and my y-axis when x is 0. So this space B is my orange lines, okay? So check 1, do we contain the origin? We do. Check 2, if I add any two things on these orange lines, am I still on the orange lines? So for example, if I add this and this together, we add them tip to tail. So I would end up here, and that is not on either of those lines anymore. So this is not closed under addition. So an example where this would not be closed. So now to talk about this being closed under multiplication, if I have any vector in either of these lines and I multiply them by any number, we will stay on the y-axis, or if we start on the x-axis, we'll stay on the x-axis. So this is closed under multiplication. Alrighty. So we can also check these conditions algebraically. So if we were looking at this exact same space, but with numbers instead of graphs, the way we look at this is we first check the 0 condition. We plug in 0. We set x is 0 and y is 0. So this gives me 0 times 0 equals 0. And that's a question mark. We have to see if that's true. And obviously that is true. So it is closed under, not closed under, it does contain the 0 vector. Condition 2, being closed under addition. I'm actually going to skip this one for right now, and I'll come back to it after I do multiplication. So for closed under multiplication, what this means is some constant times xy, where we have picked an xy from the get-go that satisfies this condition. So what that means is x times y equals 0, period. This is my pre-existing condition that I picked, okay? So now using this vector, we get cx, cy. And what we're checking is if we multiply these together in the same fashion that this has, we get cx times cy, which is the same thing as c squared xy, and we're checking if this is equal to 0. Well, we've determined x and y is equal to 0. So we're going to get c squared times 0 equals 0. So c doesn't affect this condition being true at all. So that's why we are closed under multiplication, because c does not change the fact that c squared times 0 is 0. Okay. Closed under addition is tricky. So there's a few different ways that we can talk about this. All right. The way I'm going to do this is I'm going to pick a u and a v. I'm going to zoom in down here. I'm going to pick two vectors, u and v, that start in my space. So I'm going to write these as u1, u2, such that u1, u2 is equal to 0, and v1, v2, such that v1 times v2 is equal to 0. I'm picking these two vectors to start in my space. okay, to start with the condition being true. So now I'm asking if u plus v satisfies the condition as well. So we add u plus v, no, that's a u. We add u plus v and we get u1 plus v1, u2 plus v2, okay? And now to check if the condition is true, we multiply our x and our y, gives me u1 plus v1 times u2 plus v2, okay? And we're checking if this is equal to 0, okay? So we've picked a u1, u2, and a v1, v2 such that each pair has at least 1 0 between them, which would be true such that they multiply to be 0. So either either u1 or u2 is 0, or they're both 0, and either v1, v2 is 0, or they're both 0. So between each pair, there's at least 1 0. So is there a way I could pick this condition to not be true? Well, I could pick my u1 to be 0, and I could pick my v2 to be 0, and then I get v1 and u2 left over. And then I'm going to be left with v1 and u2, right? So the question is this equal to 0? It can be, but it also can not be. So what I mean by that is we can pick like u to be 0, 1, and v to be 1, 0. And when we add these two vectors together, we get 1, 1. And when we multiply 1 times 1, this does not equal 0. Okay, so that's what I'm doing is I'm picking my zeros carefully to get this to be true, or to get this to be proven false. So since this doesn't necessarily have to be 0, we don't consider it closed under addition. Another way you can do this is if you want to FOIL it out, you're going to get u1, u2 plus u1, v2 plus v1, u2 plus v1, v2 equals 0, question mark. And we decided from the get-go that u1, u2 is 0, and v1, v2 is 0. So now, is there a way to pick a u1 and u2 such that one from each pair is 0, but this equation is non-zero? And the answer is yes. You can think of it just like these vectors here, okay? We pick u1 and v2 to be non-zero. And then we pick these, maybe we pick them both to be 1. And we pick v1 and u2 to both be 0. So again, this is no longer 0. So that's why it is not close under addition. So again, if you're seeing a space and you can tell that it's a column space or a null space, you know it's a subspace. You don't really have to consider anything else. Likewise, if it's talking about a solution set to an equation that is not equal to 0, it is not a subspace right off the bat. Okay. So now let's move on to talking about onto and one-to-one. Actually, what I'm going to do first is talk about domain, codomain, and range, and then we'll talk about onto and one-to-one, because I find it easier to explain those with domain and codomain. So in this class, we use the equations ax equals b. That's what we're talking about for a matrix equation, right? So we're transforming from x to b by a, all right? So we're starting in some space, call this blob, the places where x's can live, okay? This is all of my possible x's drawn out, all right? In this blob over here is all of the places my b's can be, all right? All of my possible b's, not all that we're consistent for, but all total b's. And we're getting there by some lens. Let me redraw that. And we're getting from the x to the b by a. What I mean by that is we take an x and we go through the lens, and the lens reflects this somewhere, and we get an output b, okay? So we define the space where x's are as the domain. And this is always r to the number of columns. Likewise, b, when we start in our domain, but we still end in a space, but it's a secondary kind of space. We call it the codomain. That co comes from being the second part of this, essentially. So this is always r to the number of rows. Okay, you can just think kind of the duality of this. Domain is r to the number of columns. Codomain has to be r to the number of rows. Okay, so now to start talking about what range is in this case. Range is just a new word for column space, but we talk about it in this concept of like where we can reach in images. And what an image is an image is if I start with some x, my image of x is what b I can get. It's what happens to x as I go through this lens of a. So if I take every single x and I plot all of them somewhere in this, I take all of their images. Okay, all of these individual dots are going to make a shape, and that shape is going to be just some blob. Okay, it can never be bigger than the codomain because it has to be within it, but it can be at most the codomain. So this whole space we call here, we call the range, which is always number of pivots dimensional in R to the number of rows, because it's a subspace of our codomain. Column space is a subspace of codomain. That's important. Okay. Now, I'm going to erase these, but keep the blob over there. All right. So once again, this is our range here. And what range also means is if my b is in here, I am consistent for ax equals b. If my b is out here, I am inconsistent for ax equals b. Okay. So some other space that I like to talk about is the null space. Where does the null space fit into this? The null space is a blob in our domain so that everything in every one of these x's that's in that blob gets projected to the exact same zero vector. Okay, everything in this blob when we multiply by a goes to zero. Okay, that's what a null space is. We put this blob through here and it reflects everything down to just be the 0 point. Okay. And what is true is for any other point, any other b, there's going to be an identically shaped blob somewhere else that everything here is going to correspond to all of the points that line up to that. So this is what we would call the solution set to this particular b. Okay. So again, to write that out, this is my null space. Okay. And this is number of free variables dimensional in, well, we're in the domain. So we're in R to the number of columns. So this is what domain, codomain, and range all look like in like space. Okay. So now, knowing this and moving on to talking about onto and one-to-one. So what onto means is for all b, there's at least one solution. Okay. So if you see for all b, there's at least one solution, that means that's the exact same thing as saying onto. Okay. All right. Going past this to talk about what our range would be. Our range is equal to our codomain for something that's onto. Okay. And to tell if this is true, you have a pivot. Well, you want to have as many pivots as you have rows to get your full codomain. So we want to pivot in each row. Okay. So to have it pivot in each row, let's consider the three different shapes of matrices. Okay. Can something that's wide have a pivot in each row? Sure. Can something square? Sure. Can something tall? No. Okay. So just knowing the shape can kind of tell you right off the bat if it can be or can't be. You don't know anything else without knowing more context. Okay. For one-to-one, now we're going to talk about for all. So the last one was for at least one solution. This one is at most one solution. Okay. And what I mean by that is there are no free variables. Okay. These are the other really, really important things about each of them to note, is that for range, for onto, range is codomain. For one-to-one, you don't have free variables, okay? And to tell if this is true, you'd have a pivot in each column because you don't want any free variables, right? So to look at the shapes of these, for something that's wide, this can never have a pivot in every column. For something that's square, it can. For something that's tall, it can, okay? So now what do these actually mean? So if I'm drawing my blobs like I did before, once again, for onto, what this means is as I go from this space, as I reflect in here, I'm going to be able to touch every single B in my codomain, okay? So my range is going to be my whole codomain. I can reach everywhere. There's no B I'm inconsistent for, okay? What that doesn't mean is I can get everywhere uniquely. So maybe I have, so maybe like this X corresponds to this B, and this X also corresponds to this B. That's okay for onto. Okay, the biggest point is that this whole codomain is covered. That's what onto means. Okay, something to be one-to-one, what that means is for each individual X, there's only one path we can take to a specific, or for each B, there's only one X, okay? So if I know this is my B, I know there's only one X that exists for that B. So every X has its own unique B. And this doesn't mean that I can reach everywhere, okay? But it means that each spot in my range, I can find the corresponding X because I know that if I have a B and there's only one way to get there, I can backtrack, right? So this talks about getting there uniquely. This one talks about getting everywhere. Okay. And if we have both conditions at the same time, we call that invertible. If we can get everywhere uniquely, that means that if I have a B, I can trace backwards to my X, and there's no B I'm inconsistent for. So all of my X's and all of my B's, you can go back and forth between them with an inverse. So we'll talk about that more towards the third exam. That's not super relevant right now. All right. So this is the big concept of onto and one-to-one here. Just make sure I'm not. Okay. So that's all the big concept stuff that I'd say was super relevant for this exam. Check my computer. I'm gonna do just a few computational examples. Ah, there's a bug on my screen. It's here. These are some of the questions I got asked last night that if you were there, you heard me answer them, but if you weren't, obviously you didn't. So I'm gonna do them again now. So this one says, find a matrix A whose column space is the dotted line and whose null space is the solid line. Okay, so this is a good example of knowing what a null space and column space are geometrically and being able to go backwards to the knowing what the column space and null space are and being able to go back to a matrix. And there are an infinite number of matrices A, okay? So to first talk about what shape of a matrix we have, we need to know where our null space and our column space lie. Both are lines, so that means I have one free variable, and it means I have one pivot. Okay, and by the rank nullity theorem, which just is a sidebar, rank plus nullity is equal to number of columns. Okay, and what rank nullity boils down to is the dimension of our column space plus the dimension of our null space is equal to number of variables, which makes sense. Number of pivots plus number of free variables equals number of variables. These are the exact same equation. Okay, rank is equal to number of pivots. Nullity is the dimension of our null space, which is number of free variables. Okay, so we know we have one free variable and one pivot, which means I have a it means I have two columns. And since my column space is a line in R2, it means I have two rows as well. Okay, you can also just state that if both are plotted on a plane, you know it's a 2 by 2 matrix. So here is what I'm going to make my 2 by 2 matrix A. Okay, so the way I always start these is I first find a point on my column space, and I call this my first column. So this is the point, or this is the vector 3, negative 1. Okay, 3, negative 1. Okay, I'm halfway there. I have two entries. Okay, you can pick any point on this line to be my first column. I could have just as easily made it negative 3, positive 1. That's totally fine and right as well. If you get stuck on the null space and you really can't figure it out, just copy your first column for your second column, and at least you know your column space will be right. That doesn't mean that's the answer to the question, but I'm just telling you, if you get super stumped, just do something along those lines. All right. So now to talk about null space. The first thing we always do is we just pick some point off our null space. All right. So this is the point 4, 2. It's the vector 4, 2. Okay, so I'm gonna write that over here. For 4, 2, what I need is this bottom entry to be the number 1. Okay. So to do that, I need to divide this by 2. So I'm going to make this 2, 1. Okay. And the reason that is true will become evident in a second. So when I have this, now I'm going to go backwards from parametric vector form. And what that means is I'm going backwards from having something like this. So if I write this back out in equations, I have x1 equals 2x2. I have x2 equals x2. Okay. If this number was 2 instead, okay, and I was plugging in 2 here, I would get x2 is equal to 2x2, which we do not like. That kind of breaks the math we're trying to do. All right. So that's why I'm saying first make that number 1 in the bottom entry and then go from there. Okay. Otherwise, if it is just like if your null space is just the line 1, 0, then your free variable has to just be x1 instead. But that's a very specific case. Okay. So going backwards from these equations, we have x1 minus 2x2 equals 0. And this would be where I would get from my reduced to echelon form. So that means each of my rows has the form 1, negative 2. And we don't know anything about any of the other rows below it, except they have this form. The first one, the first entry times negative 2 gives me the second entry. Okay, so going from here to here is by a factor of times minus 2. Okay, so now looking up top, we have a 3 as our first entry to get from our first column to our second column, our first column to our second column. We do the exact same ratio, 1 to negative 2. So that means this is negative 6. Okay, and there's two ways to find this bottom entry. All right. Way 1 is that it must have a similar form in a column as 3, negative 1. So if I have negative 6 instead of 3 on top, I had negative 1 here, it's going to be positive 2 down here. Okay, it's just the same ratio between the two of those. Likewise, I can instead use my null space. So this is negative 1, so this should also be positive 2. If we get the same number for both of those things, then we know we've done this correctly. Okay, so this would be my matrix A in that case. So now, what is this one? This one is a good question that talks about transformations, which you are going to need to know how to create. All right. So the big one that you need to memorize is the rotation matrix for a counterclockwise angle. And what that is that's just equal to cosine theta, negative sine theta, cosine theta. Okay. And if clockwise, instead, just make theta negative. So for example, you had a 45-degree clockwise rotation. That's the same as a negative 45-degree counterclockwise rotation. So I just like to memorize one matrix because otherwise you can get confused with some negatives, okay? And if you care, What is a clockwise matrix? What's different about it? This is instead plus, and this is instead minus. Okay. But again, don't dwell on that. I just remember the counterclockwise matrix and go from there. So this one is talking about, it's a typo. Let A be the matrix that rotates vectors counterclockwise 10 degrees. Find A to the 9th times 2, 0. Okay. So A to the 9th means we're multiplying a rotation counterclockwise by 10 times a rotation counterclockwise by 10 times, which is a lot. That's 9 2x2 matrices to multiply out. Okay. The way we can think of this instead is we're rotating by 10 degrees 9 times. Okay. So if we're doing that, we're doing rotating by 10, then rotating by 20, 30, 40, 50. So A to the 9th is the exact same as just rotating counterclockwise by 90 degrees now. So we can plug back into what our rotation counterclockwise matrix would be for a 90 degree rotation. I'm going to get the cosine of that is 0. The sine of that is 1, -1, and 0. Okay, so this is A to the 9th is what this is. This is a rotation by 90 degrees. What this question is asking is A to the 9th times 2, 0. So we're just multiplying this by 2, 0. The way I like to think about matrix multiplication is what I do is I write the two matrices next to each other, and then I move one up so that they're corner to corner. Nope. And what I do from here is I do something my pre-calculus teacher taught me, which is called building bridges. So I connect my first column of my first matrix to my first row of my second, and so on and so forth. Okay. So what that means is I'm going to have a resulting matrix down here. Okay. And this first entry is going to be 0 times 2, which is 0, plus -1 times 0, which is also 0. Okay. Because between our bridges, we add for each entry that it is. Okay. For the second one, it's going to be +1 times 2, which is 2, plus 0 times 0, which is 0. So my resulting vector is going to be 0, 2, and that would be the answer to this question. If we had something a little bit more complicated for matrix multiplication, like maybe we have 1, 1, 0, 1 times 2, 0, 1, 1, this is 0. The way we would do this, we move this one up. We're going to have a resulting 2 by 2. We build our bridges from here to here and here to here. In my top left position, I'm going to have 2 times 1 plus 1 times 1. Because 1 times 2 plus 1 times 1. And in my first row, second column, I'm going to have 1 times 0, 0 plus. Because what I'm doing is I'm multiplying across bridges and adding between them. Okay. So for my second one, I'll have 1 times 1, which is 1. Okay. Then for my bottom left entry, I'm going to have 0 following up times 2, which is still just 0, plus 1 times 1, so plus 1. And then the same is true. The same is true there. So we can rewrite this instead as our resulting product is 3, 1, 1, 1. And that's how we matrix multiply. So I'll do a couple more. So I'll talk about this one only takes a second. So this one is, there is more on this question in the actual review about how it would pertain to a column space, but I'm just going to talk about this right now. So this is asking, consider the subspace here, and it's given that it's a subspace. And what we're looking at is we're looking at this equation. And this looks awfully familiar. This is actually just the definition of a null space. Okay. Null space corresponding to the matrix 1, -1, -1, 1, augment 0. It's very important that it's equal to 0. Otherwise, it's not a subspace. Okay. Likewise, if you have like a +1 on the end over here, also not a subspace, not a null space either. Okay. But since we can write it in this matrix like this, and we're talking about a null space, Null space is equal to the number of free variable dimension in R to the number of columns. And here we can see pretty clearly we have 3 free variables. So that means this is true. The dimension of this null space is 3D. And let's talk about what we talked about in my review last night is what would this look like if it was a column space instead? Is it would be the same first condition, but it'd be given like x minus y, w plus 3z, and then 4y, something like this. Okay, instead of like what this would look like. And this is the definition of a column space corresponding to the matrix where my rows are my equations and my columns are my variables. So this is 1x minus 1y, 0z, 0w, 0x, 0y, 3z, 1w, 0x, 4y, 0z, 0w. And what you'll find is you have 3 pivots. In this particular case of this matrix that I'm showing, so the dimension of this space would also be 3D. Now I'll talk about this one briefly. So this is from Studio a couple weeks ago, I believe. What this asks is this is asking us to create matrices based on the given conditions, okay? And as a little sidebar, whenever you see this like T from R3 to R2, this is always domain to codomain, which is always columns to rows. So it tells us the dimension of our matrix just from that. So this is asking which of the following are onto and one-to-one. If it's not onto, find something not in the range. If it's not one-to-one, find 2 vectors in the same image, okay? So to prove not onto, what you would do is you augment a matrix A with however many B numbers we need to fill the rows, okay? And we're going to solve this like we solved those H and K problems to find B1, B2, B3 to make it inconsistent. So it's the same sort of idea. And this would be if something is not onto, finding that B1, B2, B3, then you write it as a matrix. Say 1, 1, 1 was like a counterexample that made it inconsistent. This would be a vector that makes that true. For something that's not one-to-one, all we need is we need 2 vectors in null space. Because if we have a null space, that means we don't have a pivot in every column, okay? So that's one way to find one-to-one, and this is one way to find onto, because if we prove we're inconsistent for something, we don't have a pivot in every row. So I'm not going to write out counterexamples for each of these, but for a clockwise rotation, this is just exactly that counterclockwise rotation matrix I said before with 32 degrees plugged in for theta. For this one, we're going from R3 to R2, so it's a 2x3 matrix. I'm just going to construct these matrices as transformations, okay? This one, we're talking about, we have 2 equations here, z and x. So my first equation is 0x, 0y, 1z. My second equation is 1x, 0y, 0z. This is onto, but not one-to-one, and you can go from there about how to find vectors in the null space. Likewise here, very similar, pretty much the exact same question, but instead my first equation is all zeros. My second equation is just x. For this matrix, you're going to get something that row reduces to look like this. So this is one-to-one, but not onto. And for this one, it is neither. So that's what that would look like. Okay, let's talk about this one. So for this one, it's asking, find the basis of a column space, and they've already done the hard work for us and put this in reduced row echelon form. So we have our pivot columns of the original matrix. So it's going to be 2, 3, and 4. And 7, 10, and 12 form my basis because they're just the pivot columns of the original matrix. And then write a new basis for column space of A so that no vector in our new basis is a scalar multiple of any of the vectors in the basis that you wrote in part 1. So a way you can kind of picture this is if we're in R2, we span all of R2, okay? This vector and this vector span R2, but so do this vector and this vector, or this vector and this vector. All of these pairs span R2. So this is just asking to find a different pair that still spans the plane created here. And an easy way to do this is we kind of just do u plus v and u minus v. And what that means is these create a plane. So to find any other two vectors on this plane, they're just linear combinations of these two. So I could do 4u plus v, and I could do 3u minus v minus 10v. Those are still valid vectors, okay? We're just looking for two different linear combinations of these two vectors is essentially what this is asking. Okay, last little special condition to talk about here. So what we have here is A is 3 by 4 and B is 4 by 5. Okay, so the transformation is A times B. So we have the way I like to write these is A times B is a 3 by 4 times a 4 by 5. And I put a box around my middle one to see if they can connect. And then my resulting matrix is going to be a 3 by 5. Whatever numbers are outside of that box. So the null space of AB is at a subspace of R4. It is not, because it is in R to the number of null space columns. Okay, so that is in R5, not R4. Okay, all right. So now let's talk about 2. So this is just, I'm not going to spend too much time on this, but essentially the equation you need to remember is the column space of A is always greater than and contains the column space of AB. And the null space of B is always contained and within the column space of A. I wrote the column space. That should be the null space. Null space of AB. So what I mean by that is column space of A is the biggest the column space of AB can be. It can be smaller, okay? It doesn't have to, though. So this is saying every vector in, oh, sorry, this is backwards. In the column space, also in the column space of A, that has to be true because it's always contained within. So this is true, okay? And another way we can write these equations is the number of pivots in A is always strictly greater than or equal to the number of pivots in AB, and likewise the number of free variables in B must always be less than or equal to number of free variables in A, B. It's the same kind of duality of they have the opposite sign, one's talking about pivots, one's talking about free variables, everything like that. So just like kind of know these equations. They come up in a few different cases of like short answer and true or false and things like that. The last one is T cannot be 1 to 1. So it is a 3 by 5 matrix. So it is wide, so it cannot be 1 to 1. So that is false. We'll do one more. Actually, I'll just do this one because it ties into this really well. Okay, so I'm just going to rewrite this question, but it'll be asking the exact same thing. Okay, I'm just making it a little easier for myself. I'm going to make this m less than n, and I'm going to make this a and b. Okay, so this is given that a is m by n and b is n by m. Okay, so if m is greater than n, that means a is tall. Okay, if it's tall and it's m by n, that means I can have at most n pivots. Okay, but a times b, which is m by n times n by m, check the box, we get an m by m matrix. Okay, where m by m, and by this condition, the number of pivots here can be at most the same as it is in A, okay? So this can have at most n pivots, okay? So let's call maybe m is 5 and n is 4. That means I can never have a pivot in every column. So this is, and using the condition that m is always greater than n, we will always have more columns than pivots. Our columns must always be dependent. We can never have a pivot in every column for this particular case. However, if we go the other way, if A is instead wide and B is tall, A can now have at most m pivots, okay? And we said that A times B is still m by m, okay? And we can have at most m pivots. We can have independent columns. We don't have to because we don't know everything about it yet. Okay, so they can also be dependent because A and B could just be the zero matrices. All right, last one. Okay, the first one. Let B be the set of all vectors of this form, where x is any real number. Is this a subspace? You can do this a couple ways. You can check each of our conditions. You can think about it geometrically. This is just going to be the x-axis, which can also be defined as the column space of the matrix 1, 0. And since it's a column space, it is a subspace. Check. Is it in R2? Well, we have 2 entries, so yes. And I'm not going to work out the other ways you can do this. You can kind of spend your time doing that if you'd like. So let W be the following space that corresponds to all solutions, okay? The big thing here is we're not equal to 0, so this is never a subspace right off the bat, okay? All right, 3 says A is 3 by 3, okay? Must be true that the solution set to the equation x equals 0, the null space is a subspace of R3. Well, the null space is a subspace of our domain, which is our number of columns, and we have 3. So it is a subspace of R3. That is correct. We don't know what shape it is, but we know it's a subspace. And the last one, suppose we're going from R2 to R4. So we have a 4 by 2 matrix. Must it be true that the range is a subspace of R4? This is basically the same thing as the last question, but with a column space instead, because range is just column space. Okay, so is it a subspace? It's always a subspace, but the question is it of R4? The answer is yes, because that's in number of rows. Cool. All right, thank you for watching, and I wish you luck on your midterm.